All right, geometry. Starting a new chapter here. This one's on this first section on polygons and their the angle measures and whatnot. So you see a couple figures here. Polygons basically are just like figures. This one we have a pentagon on the left there, 5 sides, and then I think that's 8 sides on the right, octagon. So things like that. There's some properties about their angle measures and whatnot. So let's dig into it. So there's a theorem saying the sum of the measures of the interior angles. Okay, so the interior angles, we'd have angle 1, 2, 3, 4, 5 angles in there. Okay, and if we were to add up those angle measures, that would be obviously the sum. So the formula for that is n minus 2 times 180, and the n is basically how many sides these figures have. Okay, that's why this one's just an n-gon. It could be like a pentagon, or they could write it as a 5-gon or whatever. N is again the number of sides. Okay, so they just use n-gon. If an octagon would be considered an 8-gon, that kind of thing. And so why is it n minus 2 times 180? So the idea is, if you think about, if we were to divide this into triangles, right, we'd have 1, 2, 3 triangles. In this example, n was 5, right? It was a 5-sided figure. It had 1, 2, 3, 4, 5 sides. So the number of triangles formed is always 2 fewer than that, okay? And each triangle has 180 degrees. So that's why in this case, the total sum of the angle measures would be 3 times 180. Okay. Similarly, on the other figure, it has 1, 2, 3, 4, 5, 6, 7, 8 sides. And when there are 8 sides, we could get 1, 2, 3, 4, 5, 5 like kind of diagonals there, they're called, which would create, as we can see, 6 triangles. Okay, and each triangle would compose of 180 degrees. So 6 times 180 will give us the angle sum. Okay, so this little formula, you might want to start a list or whatever where you have the formulas. There's a few in here. But this is one way to find this is the way to find the sum of the measures of interior angles. Okay, so it's always that n minus 2 times 180. So let's do an example where we're using it. Here's a diagram here. Let's see, how many sides do we have here. We have 1, 2, 3, 4. This is a 5-sided figure, a pentagon, right? They give us 4 of the angles, and we need to find the 5th. So what we need to figure out is the total sum of the angles. Okay, I guess we don't need the word total, but we'll just leave it there. The sum of the interior angles. In this case, n equals 5. It's a 5-sided figure, right? It also has 5 angles. So the interior angle sum is going to be the n minus 2 times 180. Right, so 3 times the 180 is going to give us our angle sum. In this case, it's going to be a total of 540 degrees. Okay, so I know that the sum of all 5 angles need to add up to 540 degrees. So what I'm going to do is just add up the ones that they gave me and subtract that from 540. Okay, so adding those 4 up gives me 456. Okay, so if I subtract 456 from the 540, that should give us our value of x, which in this case is 84 degrees. Okay, so you can actually find missing angles just by knowing the sum of the angles. It's kind of like you would do in a triangle, right? In a triangle, we would know there's a total of 180 degrees, so if they give you 2 of them, you can just subtract those 2 from 180. This is the same kind of thing, okay? Okay, so next thing here, this is a corollary. It's basically just an extension to the theorem. And the theorem was just saying the n minus 2 times 180 thing. Now this is saying if the n-gon is regular, so first off, to be regular, we need to know what that means. And what that means is that all sides are congruent and all angles are congruent as well. Okay, so it's a regular polygon, like a square would be regular because the side lengths are all equal and the angles are all 90. Maybe we'll use that as an example. But a rectangle may not be, right? A rectangle might have a long side and a short side or whatever. Or with triangles, equilateral would be regular because all the angles and sides are all the same. But isosceles may not be. Okay, so what it's saying is if the n-gon is regular, then the measure of each angle, okay, is going to be the n minus 2 times 180 over n. So it's really just saying, you know, the numerator of that is just finding the angle sum. And if you think about it, if they're all the same, you could just divide by how many there are, right, which is dividing by n, and that will tell you how large each one is. So for example, let's just say we have a square. Okay, and let's say those are all equal to each other. Just to kind of see a quick visual here. And let's say we didn't know what the angle measures were for whatever reason. Okay, so we know that in this case, n is 4, right? There are 4 sides and 4 angles. So what this little corollary tells us is that each angle is going to equal the n minus 2 times 180 over n, which is 4. And really all it's doing, again, the numerator is just finding us the angle sum, right? And so the numerator is just 2 times 180, which is 360. That's the angle sum, and then when we divide that by the 4, that's going to tell us that each one needs to be 90 degrees. And we knew that was true for a square, but this is just a way to show it. Okay, so let's look at another example using this. Let's say they tell us the measures of each angle, each interior angle, okay, because again, these only work for interior angles. We'll talk exterior in just a minute, is 165 degrees, okay? How many sides does this thing have? Okay, so here's the thing too. Since they're telling us the measure of each angle is 165, they're kind of telling us it's regular, right? They're telling you all the angles are the same of 165, and that's going to kind of imply that the sides are all the same. So if each angle is 165 degrees, how many sides are there? So let's use that formula that we just saw. It said n minus 2, right, times 180 over n. And we know in this case they're telling us the measure of each angle is 165 degrees. So let's set that equal to 165. And what we're going to do is we're going to solve for n, because n is the number of sides, and that's what we need here. So how would we solve this equation for n? Okay, first thing, notice there's 2 n's in the equation. What I would do first, since there's an n in the denominator, let's multiply both sides by n. Okay, and get rid of that n in the denominator. So n minus 2 times 180 is going to equal 165n. And now we can just go ahead and try and solve this thing. Let's see what happens. We'll, on the left side there, let's go ahead and distribute the 180. So 180n minus 360 equals 165n. Okay, and then trying to finish this out here, we could then subtract the 180n from both sides and get negative 360 will equal negative 15n. And when we go ahead and divide both sides by negative 15, you should end up with n equals 24. Okay, so that's a 24-sided polygon. Okay, it would be hard to draw that, okay? But if you could draw a regular one where all the sides and all the angles were the same, every single interior angle would need to be 165 degrees. Okay, so let's keep moving on. There's a separate theorem now. So those problems we're all talking about, again, the interior angles. There's also a little theorem about the exterior angles. So you see in the figure here, let's see, here's some polygon. Let me try and highlight that a little bit. So this is a pentagon, right? 5 sides. And of course there are 5 interior angles, but there are also 5 exterior angles formed, and I numbered them 1 through 5. If you can like imagine the sides continuing on where the dotted lines are, you get these 5 exterior angles as well. And the rule here, or the theorem, says that the sum of the measures of the exterior angles, if there's one angle at each vertex, okay, as shown, is 360 degrees. So that sum is going to be 360 degrees. So if we were to add up the angle measures, angle 1 plus 2 plus angle 3 plus angle 4 plus angle 5, the sum would be 360 degrees. Okay, so let's see if we can put that to use and do some problems with it. Okay, actually first off, let's do a quick, forgot I put a quick visual in here. If you see the one on the left, so that is obviously a triangle, the yellow figure there, and it appears to be equilateral. So the angle measures in an equilateral triangle would be 60 degrees each, right? Okay, to get 180. So that would make, if we thought about the whole supplementary and that kind of thing, look at angle 2 right here would have to be 120 degrees because the 60 plus the 120 form a straight line, right? They form a 180 degree angle. Same thing with angle 3, and same thing with angle 1. And what the previous theorem told us was that the sum of the exterior angles is 360, okay? And that shows it. All right, similarly, look at an example with a rectangle, right? In a rectangle, we know we have 4 right angles, right? Boom, 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 boom. So using the same idea, each of these angles, because they're forming straight lines, would need to be 90 degrees. Okay, and if you notice again, the previous theorem just said the sum of the exterior angles, angle 1 plus 2 plus 3 plus 4 equals 360. We have 4 angles of 90 each. They equal 360. Okay, so that's just a quick visual. Let's do an example where we can actually do some work on our own. Okay, so here's a figure. Looks kind of like a parallelogram maybe. And we have some angles designated y and 2y, and we need to find the value of y. Okay, so if we think about what the theorem said, right, this is an exterior angle, this is an exterior angle, this is an exterior angle, and so is that one. So we have all 4 exterior angles, and what did the theorem say? Okay, the theorem says the sum of the exterior angles must equal 360, no matter how many sides there are, right? So we'll do 2y plus y plus 2y plus y equals 360. Okay, so this one does not depend on n. It doesn't matter how many sides there are. The sum is just always 360. So if we combine those like terms, 2y plus y plus 2y plus y, we have 6y's, right, equals 360 degrees. Divide both sides by 6, and y must equal 60. Okay, so that's using that theorem there. Okay, and this theorem has a little corollary to it as well, similar to the last one. So again, if the angle sum, right, of the exterior angles is 360 degrees, what this corollary says is that the measure of each exterior angle, okay, of a regular n-gon, okay, it's got to be regular again, just like we saw the corollary before. If they're all equal, we could just take the sum and divide by n to get how large each one is. Same thing's going to apply here. So it's telling us the measure of each will be the 360, which is the sum, divided by n. So let's kind of visualize this. Sometimes it's a little tough to see this. But let me go ahead and first off extend these sides out here. Let's extend that a little bit. Boom. Just so we can see where these exterior angles land. Okay, so you'd have angle 1 here. We could have another exterior angle right here, right here, right there, and right there. Okay, so those are your 6 exterior angles. Notice the vertex of them is the vertex of the polygon itself, right? Okay, and what this theorem is telling us is that angle 1 would equal angle 2. I guess we should use the congruent, would be congruent to angle 3, and so on. And each one of them would equal 360 degrees. In this case, divided by how many did we have? 6. So in this case, each one of those angles would be 60 degrees. Okay, that was the n for this specific problem because it had 6 sides. It had therefore 6 exterior angles. And again, this only works if the polygon's regular, meaning all these side lengths are equal to each other, and each interior angle is congruent. Okay, and we could see how to find those values using the theorem from the beginning of the section here. Okay, so hope that helps. A couple theorems again, I would have them written down. Just kind of keep them organized and next to you when you're doing these problems. The problems are generally quick, okay, as long as you know which property or theorem to use. All right.